Hello, this is our first meeting after a break caused by the present coronavirus situation. And as you might remember, we have been talking through our previous lectures about the mechanics. And today we start the other chapter of physics, which is the fluid dynamics. Fluid dynamics is a very fundamental part of physics, and it used to be even more in previous centuries. And since it was growing up very rapidly, it eventually has become a completely independent science. And you have a fluid dynamics department. Occasionally it's called the hydrodynamics, but we will be using the word fluid for most of what we are talking about. We will be talking about refers not only to the fluid which are in the common language called liquids, like a water or a blood or other biological liquids encountered in animals, humans, but it also deals with the properties of the, for example, air. The fluid dynamics and its mathematical apparatus, which is incredibly large and very sophisticated, has become a working tool for the nowadays extremely important part of science, which is called the climatology, for all those fantastic simulation of weather predictions, which we hear every day on the radios, or those occasionally very frightening predictions about what will happen to the world climate and what we can expect from the present development of a climate is also obtained by solving fluid dynamics equations, mostly numerically on a big computers. We will begin our lectures with a short discussion what are fluids, and as I said, the fluids are liquids, gases, and substances which are defined conventionally as those material systems which do not keep their shape if they are left alone. That is, if we will remove the container or walls which surround the system, it will not be able to keep up its shape. That is, of course, a very primitive definition and not truly correct, for I believe it's still possible that if you will go to the toy store, at least they have it in this famous store Toy for Us, which is, as far as I understand, gone from our country, then you could have purchased a toy which is called the silly putty. And that was a little plastic container which was filled with a substance which you can form in the shape of a sphere, and when you throw it to the floor, it bounces up like a rubber ball. But if you will leave that silly putty in a glass and keep it overnight, when you will wake up in the morning, the silly putty will fill up the container as the liquids. So that is the kind of a material which is also, you can manufacture something like this at home by measuring the wheat, the kind of a wheat made out of potatoes, with the water, and you will basically will be able to perform several experiments with the substance as with the silly putty. These are liquids which are behaving for a very short time processes as almost solid, and for long time processes, as slow processes, they become as they will behave like fluids. And what is short time, what is long time, is determined by a certain characteristic time scale. So as we will see, these materials are, in addition to many properties of ordinary liquid with which we will start, are also equipped with another characteristic parameter which sets up that time scale. What is important for biological application is that the human blood, and actually blood of all the living creatures, which rely on this kind of liquids to support its activities, I mean, the life, then the blood is actually also the liquid which has this characteristic properties, and we will be discussing that slightly later on. The fluids are, in fluid dynamics, we do not look at the microscopic properties of the constituent, which are constituents of the liquid. Of course, we all know that the liquids consist of atoms or molecules from which it is built, but in a liquid physics, we are basically ignore that fact. We are looking at the macroscopic properties, and that is sufficient to describe a tremendous variety of phenomena which are happening in nature. At the end of the 19th century, it becomes important to make this microscopic description of a matter, which is usually called the kinetic theory of matter, with the hydrodynamic, fluid dynamic description as a something which is continuous and without paying attention to the microscopic structure. And that has been achieved, and starting with the work of Ludwig Boltzmann and when he suggested the equation, which is called Boltzmann equation, from which we can derive from a microscopic picture the properties of the liquids, the equations which govern the behavior of the liquids, and that has continued. And there is a branch of science called statistical mechanics, which provides tools to describe this continuous description of the liquids from the microscopic structure. We will not be talking about that in our talk. So in a most elementary description of the liquids, the state of the liquids is determined by remarkably few parameters or variables, and one of them is a density, the other is pressure, and the third is temperature. And when the fluid is not at equilibrium, that is when it's moving, there is a fourth variable, which is the fluid dynamics velocity, which is of great importance. But if at the beginning, we will be talking only about the equilibrium properties of the liquid. When it is stationary, it doesn't basically move, at least it doesn't move on the macroscopic scale, while of course the constituent atoms or molecules are continuously moving. Then we have those three parameters, density, and the density is measured in units of kilograms per meter cube, and that is of course one of the variables which are telling us basically what is the force exerted on the unit of mass of the given liquids by external forces. And the density is also what we used to call in physics intensive quantity. Intensive quantity, that is the quantity which is independent of the size of the system. The total mass of the liquid is, of course, an extensive quantity, and the density of the 1 cubic centimeter of the water is actually, at the given temperature, is exactly the same density as the density of the water when we have a swimming pool container, size container. So we have to be careful in what we are talking about, distinction between the extensive and intensive variables, and that will be also very important in our further discussion, where we will be briefly talking about the heat properties and what is called the heat physics or thermodynamics in a more correct language. In addition to the density, we occasionally are also talking about the number density. That is not, this is the how many particles constituting the liquid can fit into the 1 unit of the volume. And then, of course, it is measured in the units, which is 1 over the cubic meter. The temperature is measured in degrees Kelvin, and for all practical purposes, the degree Kelvin does not differ from the degree Celsius, but the degree Kelvin is a unit of an absolute scale of temperature, and you have been surely told that it exists and what are basic properties of absolute temperature scale in the course of high school physics. So we will be returning to what actually is an absolute temperature in our further discussions. So we have the temperature, and it turns out that those variables describing a state of the liquids are related with each other, and what relates them is called equation of state. On the slide, you can see here the equation which you surely remember from the high school, and that equation is called ideal gas equation law, and it says that the pressure is a linear function of density and a linear function of a temperature, and that there is a coefficient because the temperature has a unit of a Kelvin and the density has a unit of also its own unit. Therefore, there must be a coefficient which converts it into the units of pressure, and this coefficient is conventionally denoted by capital R. And when we measure a density in moles, basically in how many the density of mole is actually the density of a volume, is actually the weight of a volume containing Avogadro number of particles, and then the R is what has been traditionally called universal gas constant, and that is the numerical value of that coefficient. All right. When the liquid does not consist of a single species of atoms or molecules, but it's a mixture of different gases, like the air. A common air is a mixture of many particles, out of which the most important one, oxygen, is a minority partner. And sure enough, in the hot summer day, when the streets are full of cars, it is really a minority as compared to all sorts of other particles, including all those particles which are we colloquially called smog, which are in the air. So then the density is measured by a concentration. That is, the concentration is how many particles of a given species are in a given volume, in the unit volume, and therefore the total number of particles is then a sum of a concentration, a number of particles of a given species. But I believe we will be not talking about the liquid mixtures in our talks. Here on this slide, you see the table which gives you a certain feeling about the values of this of the particular parameters of the liquids. There are a few of them here, and the last one in this table is of course not a liquid, it's a diamond, and I just have included that in the table in order to show you what are the differences between the solids, which are described also by a certain branch of not the fluid mechanics, by continuous media mechanics, which traditionally was called elasticity theory. And you can see from the table the differences. All right, so we are now going briefly to discuss the equation of state. Since we have these three variables, the equation of state, the general equation, relates those three parameters with each other, so I can always write it as a certain function of those three variables, and the equation of state is that this function is equal to 0. Then and I listed on this slide few equations of state. The first is this ideal gas equation of state, which we just have discussed, and you discuss it in the high school. But the same equation can be written under different form, and it's then called the caloric equation of state, where the pressure is proportional to the density, and there is this funny bracket which contains a ratio, a difference of two quantities which are called specific heat. Specific heat is actually how much energy you have to add to the given material object, like the liquid, to raise its total energy per unit of a temperature per 1 degree. And it turns out that this amount of energy depends on whether we have the liquid, we keep the liquid at the constant volume, that in this case we denote it as a C with the subindex V, or at the constant pressure, where we keep the pressure constant. And the last equation is, and that's also, and but so these are the ideal gas equation of state. However, it turns out that there are more properties of the liquids than they can be described by the ideal gas, the ideal liquid equation of state. And the people have been trying to find out the equations which are better. And one of those equations, which we will be discussing in a moment, is called the van der Waals equation. But before that, I would like you to remember, to recall your, or refresh your memory about the pressure. We know that the pressure is actually defined as a force acting on the unit area of a given material system. If I have a liquid in a glass, then that liquid exerts tries to get out, so to say, out of that container, and exerts a force on the walls of the container. And that force per unit area of the wall is called a pressure. So in units is a force in newtons per area, which we measure in meters square. So we have so the unit of the pressure has its own name. It's called Pascal, to commemorate one of the most important philosophers of all times, French philosopher Blaise Pascal. And the unit is 1 Newton per 1 meter. But we are having also the not official, so to say, units, but the traditional units in which pressure was measured. And one of them is atmosphere. That is a unit in which people measure the pressure exerted on the surface of the air by the air contained on the surface of the Earth by the air contained in our atmosphere, and that is given here. And as you see, it's a huge number in pascals. So that is the reason why, if you listen to the evening television broadcast of what will be the weather tomorrow, the presenters always give you the value of a pressure in hectopascals. That is in hundreds of pascals, and then the pressure is hundreds of pascals, not this huge number. And there is also the addition unit, which is very, very traditional, to commemorate the distinguished Italian researcher Torricelli, who was the first to measure the pressure using a pipe with the mercury and container with the mercury. That, of course, is now completely forbidden. We are not allowed to use even a sealed mercury thermometers, although we are still allowed to use the mercury containing fluorescent lights to lit our homes. And actually, what is dangerous from mercury is the vapors of a mercury, and the vapor. If you break the mercury thermometers, there is very little vapor there. So unless you do something really crazy with those drops of mercury from thermometer, they are completely harmless. But if you break the fluorescent lamp, then you have a lot of mercury vapors in your home. And strictly speaking, you should have called a special chemical units to clean up your place. So the one Torricelli is 135 pascals, and that is the unit which is used in biological science, particularly when you use a pressure meter to measure the pressure of your blood. When you go to a doctor, then this number 120 or something, that is the number given in Torricelli's. All right. Here I would like to refresh your memory about the fundamental law, which is called the Pascal law, and which tell us that if I have a certain volume of a liquid, then the pressure is actually identical inside of that volume. If the whole volume of the liquid in each point of the liquid, and also that pressure is isotropic, that is the same in all possible direction. If that container with the liquid is put up in the external force, like a gravity, then of course there is a difference of the pressure on the top and on the bottom of the container, but that difference is due to the external force applied to the system. If there are no external force, or if we are considering as relatively small volumes of liquid, then the pressure inside is everywhere the same. That, of course, must be really a small volume of a liquid. And for example, we will be solving a problem of what is the difference of blood pressure in our body when we are standing. When we are lying flat, then of course all our body is at the same level. Therefore, there is no difference between the gravity force acting on our head and on our feet. But if we are standing up, then there is this 1.70 m or 1.80 m, or in the case of the famous basketball players, more than 2 meters difference from our head to our feet, and that has a considerable that causes a considerable difference in the pressure of the blood in the blood vessels on the lower part of our body and on the upper part of our body. This is an application of the Pascal law. It's a hydraulic lift. We have two containers containing the same liquid connected with a pipe, and when we apply a pressure to the container to the left, which is a container with a very small area, therefore the force which we apply there is to cause a given pressure in the small container is relatively small, namely the product of the force times that area is just that pressure. And when, because of the Pascal law, the same pressure is in the liquid in the huge container to the right, and then of course the total force this is that pressure times the surface of a much bigger surface of the upper wall of that bigger container, then the total force acting on that surface is much larger, and that was how the hydraulic lifts have been built. Nowadays, most of the lifts are powered by electricity, so you cannot see it. But I do remember times when for example, car garages which are fixing the cars, the lifts to lift the car to be able to work underneath were all hydraulic. All right, this is just to show you that how the equation of state looks in its full glory. You remember that it is a relation between three variables. So the equation of state is actually defining a surface in a three-dimensional space with dimensions pressure, temperature, and volume, as on this drawing. And the ideal gas equation of state is that surface, which is shown here. If there will be a different equation of state, that surface will be much different and might have also complicated shape. This is a sketch which shows a true equation of state for a real liquid, not ideal liquid. The liquid which is a cut through the equation of state surface through the plane which is labeled by pressure and temperature, and we will be briefly discussing those properties. All right, consider this. There are lots of lines on this diagram, and there are also the areas, and they divide the complete plane, pressure and temperature plane, in different areas. And these areas are labeled gas or liquid. And if we look at this right part of the liquid, ignore the ideal gas. This is only for a purpose of recalling how the equation of state for ideal gas looks like. Then if we move at the constant pressure over increasing the temperature, we start from a point in the liquid and we hit the line which is called the vaporization line. And that is a line on which something is happening, namely the liquid changes into the gas, the vapor or a gas phase of the same substance. What is changing here is that the density jumps. The liquid is denser and the vapor is less dense. And remarkable thing is that both of those substances have a certain symmetry and both of them have the same symmetry. What is that symmetry? That symmetry is a full symmetry of surrounding us space in which I'm living. Our space, empty space, is invariant with respect to rotation when we are in the completely empty, huge container, and if we rotate by arbitrary angle, we are not able to tell that we are not in the same position as before, and that means that the empty space is invariant with respect to rotation in all possible, with respect to all possible axes. The same refers to the translation. We can move in that huge, mathematically infinite container to the left, to the right, and we will never be able to tell the difference. So that is the property of the liquid, and the same is the property of the gas. So these two substances do not have a different symmetry, but there is a curious thing. If we continue from a point in a liquid plane, in a liquid portion of the plane, and end up in a point of the gas portion of the plane, then we have to cross that line, and over that line many properties of the liquid, like a density and many of the parameters, suffer a jump. But if we move from the same point and we go up, then all of a sudden we are found in a region where we can go over this line, because this line ends up in a point, and we end up in a vapor side point without crossing the vaporization line, and nothing is really changing. So this particular point, a critical point, is a point which we can surround by a continuously transforming liquids into the vapor. And that elementary discussion of a important phenomena in physics which are called the phase transformations. The phase transformations are of the first order when the properties, important properties of the system suffer a jump by crossing certain line. And that is a transition from liquid to the gas is a first order phase transition. But all the phase transitions which have a critical point in here are continuous phase transition, and the changes of the properties going over around that point changes in a continuous way. These critical point transitions are in a certain sense more important as the first order phase transition, although the first order phase transition are of course extremely important in applications. So let's continue now our trip from the point in the liquid portion of the plane, to the left. We will be then crossing the other line, which is a line which we called melting. When we cross it, the substance changes and becomes solid. And a solid is a substance which does not have a full symmetry of the space as the liquid or a vapor. For the solid, although it consists of the same atoms and or molecules as the liquid or its gas, arrange those particles in a very orderly fashion and arrange them in a structure of a lattice. The atoms or molecules sits in the corners of a space lattice, which has a often very peculiar symmetry. So the first order phase transition, which is when we go this way from liquid to the solid, is called crystallization. And when we move from a solid to the liquid, it's called melting. That line is also the line of a first order phase transition, but on which a symmetry of a system is drastically broken. It goes from a continuous symmetry to, mathematicians call it, a discrete symmetry. And therefore, this kind of a transition is notoriously difficult to describe. And truly speaking, we do not really have a very satisfactory theory of a crystallization, in spite of the fact that we are working on it very quickly. So now we are on the solid side of the phase diagram. And when I move now, keeping up the temperature fix and down, lowering the pressure, I can come and cross a line which is called the sublimation line. That is where the solid goes over the gas. It's vapor immediately without the interfering liquids. And you might have seen such a phenomenon if you will go to the drugstore and purchase those substance which is called the naphthalene, which is used against those little I forgot those flies which lives in a material, in a wool or something, and we put this thing, and when we keep the crystal of this naphthalene out of the cupboards in the empty space for a long time, you realize that it disappears. It sublimates. It goes from a solid phase into the gas phase immediately. So that is the phase diagram of the liquid. And fortunately for a physicist, this is the diagram which is not truly holding for at least for one existing liquid in the Earth, liquid helium, at the very low temperatures. And at the very low temperatures, a helium exhibits unusual properties, the properties which were discovered at the turn of the 20th century by people working in the Kamerlingh-Onnes laboratory. Kamerlingh-Onnes was a Dutch physicist who discovered that when you cool a piece of lead, a wire of lead actually, to a very low temperature below a few degrees Kelvin, then all of a sudden that piece of metal loses its resistance property and conducts electricity without any resistivity, and he called it superconducting metal. And to cool that metal to such a low temperatures, he needed a cooling method, and in the process that he invented the devices which allowed us to liquefy helium, and that liquid helium exhibited enormously complicated properties, but that was basically the only substance existing on the air. Liquid helium, the helium is an isotope, has three isotopes, helium-4, which is that one I'm talking about. There is also the helium-3, which is produced in the nuclear reactor, and also we can manufacture a minuscule amount of a helium-6 isotope. And we know that the helium-3 properties are even more exotic than the properties of the liquid helium-4, and we have not been able to do the macroscopic experiment with helium-6. All right. So in order to describe real liquids with such a complicated phase diagram as I have shown you, you need some more complicated ideal equation of state, and that is already mentioned van der Waals equation, and that van der Waals equation has this form, and these coefficients A and B, which differs the van der Waals equation, if they are both equal to 0, that equation will be automatically an ideal gas equation. And these coefficients are related to the properties of this critical point. Actually, they are the temperature and the pressure at the critical point multiplied by each other, but anyway, they are determined by the critical point properties. All right. So that was about the equilibrium properties, and I would like to use the Pascal law to discuss a biological application. And the biological application I would like to discuss is something which I call a hydrostatic skeleton. All right. To refresh your memory, there are basically three kinds of skeletons in biology. There is internal bone-like skeleton, which we share with many animals, which is that inside of our body there are rigid, solid state elements called bones, and our muscles attached to those bones, and with the motion of our limbs and also our total motion of our body is caused by the fact that by our muscles connected to the bones move the bones, and the bones move our limbs. And we have been discussing several applications of that in our first and second lecture. But there are other skeletons which are external skeleton, and an example of external skeleton is a snail. It doesn't have any bones in its body, but it carries, as we used to say in a children's book, its own home on the back, and that is the external skeleton of the animals. But there are also the animals which neither have an internal skeleton or external skeleton, and those animals in any case move, change its shape, and they have what we used to call a hydrostatic skeleton. All right, this is the largest animal which exists on the earth, which has this hydrostatic skeleton, and you can taste how it when you go to the good restaurant offering you the frutti di mare. All right, so let's try to describe an animal with the hydrostatic skeleton using the laws of physics. This is the element. This animal is actually a almost cylindrical or a cigar-shaped structure, which is a skin filled up with a liquid. And in that rather thick skin, it has two kinds of muscle. The muscles which are circular, going perpendicular to its longer length, and the longitudinal muscle going in the other perpendicular direction, and internal is filled up with the liquid. The size of the animal is denoted by L, and the radius of the animal I denoted by small case L. We are interested in our calculation with the effective area of the circular muscles per unit length of the animal, and I will call that effective area A with a little subscript m. We remember that from our previous lectures that biologists were able to measure the force per unit area of a given muscle, and that was described by a coefficient which we labeled capital S. Therefore, the force which a given muscle per unit length can exert in those animals is this unit S times that area. All right. So the unit of that force is a Newton per meter. So let's now consider a sketch, ideal sketch of the body of that animal. It is a cylinder, and we have its skin, which are those thick black lines, and there is an external pressure exerted on the animal, which is balanced by an internal force within the body of the animal. The external pressure exerted on the animal is a pressure times the area, and the area is, of course, the area of that part of the cylinder. But because the Pascal law, it is the same pressure as it will be exerted on the surface of the rectangle with the length L and the other edge with the length equal to twice the radius of the animal. So the total force caused by this pressure is 2R times L times P. And there is the internal force Fm, which we want to calculate. And sure enough, this is described by the following equation. This internal force acting on the same fictitious cut through the body of the animal is twice F times L. So out of these equations, it follows that I have the following inequality. Then I can solve it, and I have the relation between external pressure and the force Fm. And as you see, this force is proportional to the area of a muscle per unit length and inversely proportional to the radius of the animal. So with that formula, I can calculate that force, that pressure, for a particular animal with a hydrostatic skeleton. And let's assume that the radius of the animal is about slightly less than half of the centimeter, and the area of a muscles in it, I took it from Wikipedia, and unfortunately I forgot the name of that animal. I'm sorry. And we know that the coefficient S is about 70 newtons per meter square. So with that, I can calculate that pressure, and that pressure is about slightly less than 3,000 pascals. All right, so that is a pressure inside of the body of our animal. But this animal has also the ends. It has the top end and the bottom end, and I don't know whether we can call it head and tail, but anyway, it has this clearly. So let's calculate what is the force exerted by that pressure on the upper part of the animal. And if the animal wants to move up, then it is this force which will be moving the animal. And that force exerted on the top of the animal is just the area, PR square, times that force. And that is what we can calculate. Knowing this pascals, knowing this R, you can easily calculate that force. So as you see, the Pascal law allowed us to learn a bit about how those animals with only hydrostatic skeleton can actually behave. These calculations I have done with the cylinder, I would like you to keep in mind, because we will be using very similar calculation when we will be talking about the solids to discuss a property of some nice property, because you see this kind of a cylinder which is filled up with the liquid and surrounded by the wall, you are often using in the common life. This is called a Frankfurter. The Frankfurter is actually a cylinder which is filled up with a liquid, because whatever they add to the internal of the sausage, it's basically a water. So it is precisely like this, and we can use basically the same calculation I showed you before to calculate what is the force acting on the Frankfurter wall and we will have to also be equipped with what is called the Hooke law, describing the elastic property of the wall, and we will find interesting properties, what happens in the wall of such a cylindrical object. All right, so now we are ready to go to another important hydrostatic equilibrium liquid property, which is called Archimedes' principle. And I'm sure you learn in the school all this basically urban legends about how Archimedes has discovered that principle, but I would like to remind it to you on a more physical example. Let's have a container with a liquid, and we suspend on top of that container a weight on a device which can measure the force with which this weight acts on the thread on which the weight is suspended. And there is a certain number we read on the dial. And we now, and this is of course in newtons, because it's a force acting on a thread. And we immerse now that into the liquid, and for the sake of specificness, I assume that this is water, so the density of water is about the ton per meter cube. So I'm sorry, terribly sorry. So it's measured, and what is happening? The level of liquids goes up, and if there is a little hole up there, the liquid will go out of the container, and we can measure that amount of the liquid which goes up, and that is of course a certain amount of water which we can measure. All right, so let's now draw the picture. This is our weight. This is a body which has a density ρ0, the density of a steel or a metal or whatever out of which this weight was made, and it has a certain volume which I denoted by V. And when the weight is of course a density of the ball times a gravity times a volume, and when we immerse that into the liquid, then we want to calculate the force acting on a wire, suspending wire on a thread, which I denoted by a capital T, and that force is of course a difference between, if there was no water, that would be just equal to the weight. But if there is a water, then there is an additional force called buoyancy force, that is why it's denoted by B, which is acting up, and this buoyancy force is the force by which gravity acts on the I'm sorry, there is an error in this equation. It should be the density of if this is 0, 0, that should be rho. This is not the same. I'm sorry, there is a mistake I misprinted this equation. It should be the density of the water times G times V. All right? And then, of course, I'm completely did it wrong, right? Then it's all right. Rho0 is the density of the material, so rho is density of what? No, this is correct. This is incorrect. So now the traction is a difference between these two forces, and this is the proper expression. This is also the confused because the here should be a rho zero, and this should be rho, not rho zero. I'm terribly sorry, but I don't know how to correct it. If we will be using a blackboard, that will be trivial. This is, you should replace that rho by the rho, and that is the weight, and that is the buoyancy force. This is rho zero, is the density of the water. I'm sorry, I misprinted. This is a correct expression. This is but this label is incorrect, and that's what causes the confusion. So anyway, the traction is a difference between the weight and the buoyancy force. And the buoyancy force is the force with which gravity acts on the amount of liquid which is displaced by that object. Very, very sorry. All right. So let's do now the calculation. Let's solve the problem. What is the density of that weight in the experiment we have discussed? If the reading of the meter before we immerse the weight into the liquid was 7 newtons, and the reading after we immerse it is 4 newtons, then we can easily calculate the traction, and the traction is weight minus the buoyancy. So that's this formula. So we can turn it around and calculate the density of a material, and it is the density of a water times the traction, and that given a formula. So if I use the numbers on the drawing, then I can easily calculate that the density of a material was 1,000. It was 1 1/3 of the ton per meter cube. So it's 30% heavier than the water per unit volume. So this is the application of the Archimedes principle. That the important part is that there is this buoyancy force. I have given you a question when we saw each other last time. That was the question about the balloon, which weighs 1/10 of the skin of a balloon, and the capsula for operators and everything weighs 1/10 of the expelled air, and it is the rope which holds it on the surface of the air is cut off, and the balloon raises. And how to calculate the acceleration of that balloon? And this is an example which I gave you this example for a solution, and I'm still waiting for the solution, which shows that the Archimedes force is actually the force which only acts at equilibrium. It is and we cannot use the Archimedes force to calculate the dynamics of the body immersed in a liquid, because in this case there is a buoyancy force acting up, and the effective force acting on that weight immersed in water is T, but we know what is the mass of this weight, and if we want to calculate what is the speed of motion, whether it falls down or up, we basically cannot use the Archimedes law, because we also have to consider in the balance of the forces the force exerted on the amount of expelled liquid, because if the body moves up, then the liquid moves down, and we have to include that into the dynamical analysis. So the Archimedes force is actually the equilibrium force, and it cannot be used in the Newton equations to describe the motion of the body. There is addition terms in the equation of motion, which reduces to what is called an effective mass. All right, but here I would like to show you the something which actually is very important in our contemporary situation. Namely, we are all interested how this coronavirus SARS-2 is propagating in the air, and whether we should wear the mask or not, and who should wear the mask, because if you are infected with the virus, when you exhale, then the virus propagates in the exhale air, and how far it goes, and so forth and so forth. And some experts got this Kabbalistic number of 1 meter, 1.5 meter, or 2 meters, where you have to keep from each other in order not to be infected by the exhaled viruses and so forth. And I found the paper published not long time ago in a distinguished journal of fluid mechanics, which is called Violent Expiratory Events on Coughing and Sneezing. And we will be talking slightly later maybe on it, when we will be discussing the viscosity of the liquid. And the important part of this calculation is that if you are sneezing or coughing, the little micro droplets which are generated in the blood by your air are containing viruses, but they have of different sizes, and those which have different sizes, they suffer different value of the Archimedes force, buoyancy force, and therefore the stream of those droplets assumes a peculiar shape, and that shape of that volume, of that beam of propagating droplets containing viruses, has been analyzed in greater detail in this paper. So we are now going to talk about the important equation, which is called continuity equation. And first, let me introduce a quantity which we will use very often. I will denote it by a capital Q, and this is a volume of a liquid flowing through per unit time through a given pipe or a channel. And imagine that you have this pipe, and it has the inlet and outlet, and there is a liquid going through it. Then, because the matter does not disappear in a pipe, or is not created in a pipe, the amount of matter per unit time which goes in here and comes out here is the same. That is correct only in the case where liquid moving through this pipe does not interact with the walls. If it does not feel any force of the acting on it by the external walls of the container. And that is also a part of a definition of the ideal liquid. It's only described by its density and temperature and its velocity, and there is no other information needed about the interaction with the outer walls, because they do not interact with those walls. So let's now see how we can proceed with a bit of analysis of it. We have the pipe. This is the area, and let's look up how much liquid goes in the unit of time when the liquid moves over a distance of dx. So the volume of liquid which moves is the area times dx. But if the fluid moves with the velocity v, that this distance covered delta x is equal to the velocity of the liquid times the unit, the lapse of time, delta t. And therefore, the amount of liquid which goes through that moves by the distance is just the q, our quantity, times the delta t. All right. So if I have a pipe which has a different area on the inlet and a different area on the outlet, then of course still the matter which goes is the same, but the product of A times V here and in here are different because the areas are different. So from that equation, very easily, we can calculate that the product of area times velocity must be the same. And that is called the continuity equation. That the matter does not, that is a reflection of a conservation of a mass. That the mass of the liquid passing through that pipe cannot be equal to zero. For those of you who likes a bit of mathematics, this is the more sophisticated form of the continuity equation. If I have a liquid and I choose a volume element containing a certain mass of the liquid, and when that propagates with the velocity v, then of course it changes its shape, but the amount of mass does not disappear, so the total derivative of the mass is equal to zero. And if we are able to do some analysis, mathematical analysis of that integral over a volume which changes in time, then we can convert this equation into the partial differential equation, which has a form of a continuity equation, but that is just in order to show you something. All right. This continuity equation will allow us to draw a conclusion which are usually called the Bernoulli equation. Bernoulli, it's interesting to recall that the Bernoullis are Swiss family of scientists, mostly physicists, and I believe it's still the case. But at the turn of a century, last century, there was still a professor of physics at one of the Swiss universities with the name Bernoulli. And Bernoulli, and let's, in order to derive that formula, let's consider a volume of a liquid, which is which is in a container in a gravity field, and let's think for a while about a certain amount of the liquid, which we denote, which I show you as this gray lump inside of the container. The liquid has a density rho, and the liquid pressure is P, and the velocity is and that let this blob move with the velocity v. Let's calculate the energy of that blob. The energy is conserved, so we know that the total energy of that blob is actually conserved. Again, if the liquid is ideal, if there are no other forces than those which were important for equation of state. So if there is no dissipation of the energy, there is no interaction with the walls, or what is very important, if the one liquid area moves with respect to another piece of liquid, then there is no internal friction in that liquid, and that this assumption we will eliminate in what is following. So let's calculate that energy. Well, this is a unit of a mass of a fluid, so it's the energy per unit volume of that blob due to the gravity. Let's denote the height of that location of that volume by y. Then the potential energy per unit volume is rho times gravity times this height. This unit of mass moves with the velocity vb, so the kinetic energy per unit mass is actually 1/2 of the density times the velocity square. And there is an addition term here, which is of the great importance. You remember that the unit of pressure is a force divided by the area. If you multiply the numerator and denominator in the equation by a length, then in the numerator you have a force times a distance, and that is the work, the amount of energy you have to spend to move the given element of a liquid by a distance L. And what sits in the denominator has a unit meter cube, so that is a volume. So therefore, the pressure is actually not only is actually, of course, the force divided by area, but it is also the amount of the energy deposited in a given volume of a liquid per unit volume of the liquid by the force causing the pressure. So I have to add to the energy contained in this unit of mass of the liquid, I have also to add the pressure. And this is a total amount of energy in that little volume, and because the energy is conserved, whatever happens in the liquid, this must be constant. And that is the Bernoulli equation. I derive it in this non-mathematical way because I would like to focus on the energy, that the Bernoulli equation is actually a conservation of the energy. And this is often presented without due respect to this very important fact. So now I will show you the application of the Bernoulli equation on this drawing. We have a pipe which has a different area, which has this narrow passage here, and we use the Bernoulli equation because the velocity, the kinetic energy, which means velocity square, and the gravity here and here are the same, then the velocity, so the pressure here and here must be equal. But what happens in this narrow passage? In this narrow passage, in the middle, the gravity is basically the same, but the velocity must be larger by a continuity equation, because the velocity times area here must be equal velocity times area here. Area here is less than area here at the beginning of the pipe, therefore it must be this velocity here in this narrow passage must be larger. So the kinetic energy of the liquid here must be also larger. Therefore, because the sum of a pressure plus this kinetic energy plus the gravity energy is constant, therefore the only way to achieve it is if the kinetic energy increases is by lowering the pressure. So if you have a pipe like this, then the pressure here is larger and the pressure here is lower. And that is the important physical realization of the Bernoulli law, and it is used in many devices. For example, if you carefully look at the surface of a plane, you will often see that it has a thin pipe which looks like a barrel of a machine gun, which is extended forward to from the wing of a plane, and that is the little pipe through which the air is moving when the plane is flying, and this device compares the pressure. And there is manometer usually which measures the difference outside of that pipe and inside of that pipe, and that allows to calculate the velocity of the plane. All right, that is the Bernoulli effect, and we will be discussing its application next time, discussing the consequences of Bernoulli equation for blood pressure in the human body when we are horizontal and vertical, and with a certain interesting consequences which are for our behavior. So that is all for today. I hope you were able to see me, and until the next week. Bye-bye.